Welcome to the UConn Mathematics Distinguished Lecture. It is my pleasure to welcome Professor Ravi Vakil to give our lecture. He is the Robert Grimmett Professor of Mathematics at Stanford University and the President of the American Mathematical Society. Professor Vakil received his PhD from Harvard in '97. And then after stints at MIT and Princeton, he's been professor at Stanford since 2001. And in fact, we have faculty who have taken graduate classes from him. I also want to mention a couple of other things. This is a book I got, I don't know, many years ago. It's called A Mathematical Mosaic, Patterns and Problem Solving. It's a beautiful book by Professor Vakil. And then there is The Rising Sea. It's a legendary, I think it was legendary long before it was published. All right, with that, I hand it over to you, Ravi.
Thank you very much. Thank you very much for that very good introduction. So thank you very much for the invitation. It's I'm very happy to be at UConn again, and look forward to being here many times in the future as well. And I'm intending this lecture for a broad audience, and hopefully with some interesting things to say, even for advanced math majors and people with a similar sense of a similar mathematical sophistication. But in particular, this isn't a research seminar, and I have no problem in boring experts. So, but I'm happy to talk afterwards in detail about the interesting topics that I have no time to get to in these 50 minutes or so. My goal instead is to get across the sense of how we think in algebraic geometry, and in particular what I find really fun, which is living in several worlds at once, because of the deep connection between some really quite different parts of mathematics. So algebraic geometry brings to bear simultaneously ideas from number theory, geometry, and topology. And my intent is to give you some glimpse of how, and I hope at the end to explain some facts at the roots of topology, this notion of Bott periodicity, which can be seen as coming from some simple algebraic geometry. And I want to mainly give you the tools that let us begin to understand these sorts of questions. So before I forget, I'm going to touch on work involving a large number of other people. I just want to make sure I mention their names in public: Melanie Matchett-Wood, Aaron Landsman, Hannah Larson, Jim Bryan, Polish Ellick, and some more. So what I'd like to do is, first of all, starting out by giving you some circumstantial evidence for some that suggests that there are connections between worlds that look quite different. So I'll tell you some beautiful facts that, if you squint and look at them the right way, show some similarities. And these are going to be things about something really very basic that you can see in high school or earlier, which are just about polynomials in one variable. But there are clues to very fancy things here as well. And then I want to give you one tool to make these links, which connects a means of connecting geometry topology by means of algebraic geometry, a way of adding and subtracting and multiplying spaces, the sort of algebra of spaces, which I can give the fancy name of the Grothendieck ring of algebraic varieties, and I'll essentially tell you what this is, but really it makes it something really concrete and not well, I won't say not complicated, but to define it is really quite simple, and you can begin to ask some basic things. And then I'm going to end, depending on time, by giving you some sense of where this leads, by telling you a bit about the surprise about periodicity and topology, and how it's secretly an algebraic fact. And then maybe, depending on time, how we got there also involves some recent work where part of the advances, it's purely mathematical advances, but they also involved exploring how one does mathematics using new tools in AI, and a recent paper where it feels like we're just playing with how we accelerate mathematical discovery. We're just, in some sense, the human race, we're just starting this adventure, but beginning to see how this works. And maybe one message I'd say is that much of the story in public about it is either dystopian or filled with ridiculous hype, and neither really seems remotely attached to any evidence. And so really, but it is an exciting time, and so we can talk about it. So let me start with some circumstantial evidence. and some facts that I find memorable and that suggest something deeper is going on. So let me start off with, as a warm-up with something that I think a reasonable minority of people in the audience would have heard of before, which is the question: why, if we give a random integer, and I take a random number, what are the odds of it being square free? It's got no repeated prime factor. So just the first thing to note to begin is that the question as it stands makes no sense, because there are an infinite number of integers, and an infinite number of them have no repeated prime factor. So the answer is infinity divided by infinity. And there's not much information. But it does make sense. And then we try to figure out how it makes sense or whether it makes sense. And so what we do as scientists or mathematicians, which is, or as human beings, which is we just explore and take evidence. So of the first 10 integers, we could simply see what the odds are that they have no repeated square factor, they have no square factor. So 4 and 8 are divisible by 4, and 9 is divisible by 9. And so I think, so 70% of them, of the first 10 satisfy that. But that's 10 out of infinity. So we haven't gotten very far. But then we might just do more, and we could try up to 100 or up to 1,000,000. And we begin to notice something, which is that this tends, which is that the numbers don't oscillate, but they do oscillate a little bit, but they somehow, the percentage of numbers which have no repeated prime factor converge, and they converge to something kind of interesting. So if you were to go way beyond 1,000,000, you see that the long-term average as a percentage was actually 60.79. This is rounded to 7%. So even after the first 1,000,000, you are awfully close. So that's of some interest that it's something, but that's a very special number that it is. And it's a number that I bet someone in the audience knows what it is. They can claim to have recognized it, but I know they probably don't for some other reason. So yeah, does someone know what that number is? Yeah, sure. Fire away.
1/zeta2.
Oh, that's even the fancy answer. Okay, great.
6/chi².
Ah, okay. You gave me both. Okay, so by lucky guess, it's 6/pi². And I will say 1/. Now the problem with zeta is I'm unable to ever correctly draw a zeta, but that's supposed to be a zeta. Okay, but it's 6/pi². And so the first time you see this, you have to, like, what is the circumference of the circle doing in this question about numbers? So there's some interesting reason for this to happen. And then for those familiar with the Riemann hypothesis or the Riemann zeta function, this is in fact 1/zeta2. And this is actually going to come a little bit, this does come into the story later, and it'll come into this part of the story that we'll talk about at least a little bit soon as well. Okay, so there's this, where do we go from here? What I love about this fact is it's the beginning of a whole, there are many directions you can go. It's the first story, first part of so many different stories. It's the first chapter in so many different books. So I'm going to take it in a certain direction. And so the direction I want to go is, I want to consider polynomials in one variable. So I want to consider polynomials in one variable. And the question I'm going to ask is just the same of all the polynomials in one variable. What are the odds that the polynomial has no square factor? And then I could have asked just with the integers, I could have said, what about no cube factor, no fourth power factor? And those would be interesting questions too. And I want to ask the analogous questions. So I want to make sense of this question. And there are a couple of things I need to do to make sense of them just to get going. And the first, okay, so just to set some sort of notation, we can think about this. If we consider the degree n polynomials, well, they naturally form some sort of space. In that degree n polynomial, let's say its leading coefficient is 1, then all we have to do is pick the remaining coefficients. And one thing I didn't really tell you is what are those coefficients? Where am I choosing them? Well, I'm going to have them be inside a field, and if there are any non-mathematicians here, we won't worry exactly what that means just yet, but I'll say what the rules are for what they are. And so, but there's a choice of, if k is my choice for each coefficient, I have k to the n choices for what the coefficients should be. So let me try to make sense of this. Let's try to think like first, like computer scientists. I want to get, just like with the integers, the problem is there's infinitely many of them. Polynomials, you might reasonably want, normally polynomials, normal people think about them with real numbers as coefficients and more, and then depending on how fancier you think you are, you might prefer the complex numbers or the rational numbers. So we'll pick, so just so we can get a finite number, so we can make actually, we can actually measure odds. Let's think like a computer scientist and work mod of prime p. So now each coefficient, everything is mod of prime p. We're working over a finite field, and more generally, we can work over any finite field for what I'm about to say. And now you can get your coefficient. If you have p, let me just go back a step so I can have p choices for each of these coefficients. So you have p to the n different such polynomials. And now you can say, what are the odds that this polynomial is mod p, has a factor, has a square factor. And now we can do something empirical. We can check out the degree 2 polynomials, the degree 3 polynomials, and so forth. And just like we did with integers, we're checking the first 10, 100, and a million. We'll get some information. And so degree 2 polynomials, having a repeated factor just means that the discriminant is not a 0. So no repeated factor means the discriminant is non-zero. And if you think about it a little bit, you can realize that the odds, if you pick two numbers mod p, b and c, the odds of it not being 0 mod p is exactly 1 in p. The odds of it being 0 mod p is 1 in p. The odds of it not being 0 is 1 minus 1 over p. And for example, if you're, well, let me just say it, but don't worry about it if you don't want to follow everything I'm saying. You could pick if you're pick b randomly, and for each b, you just need to pick the c for which this is not true. And the odds, and only one c will make b squared minus 4c 0. So the odds of it being non-zero is 1 minus 1. And you can do the same thing for cubics, and there's a formula for the discriminant of the cubic, and it's more complicated, and you'll do more work. And with a bit more work, you discover that the odds of it having no repeated prime factor, no repeated factor, the odds of the discriminant being non-zero is once again 1 minus 1 over p. And now the magic, the surprise thing, is that for any degree, once you're at least at 2, the odds of a degree 95 polynomial having no repeated factor is 1 minus 1 over p. And that is whenever the answer is super simple and it's not obvious why it's true, something interesting is going on. That's a worthwhile, highly, reasonably, quite hard exercise for people who are thinking about these things. I like this exercise because for people who are near these fields, there are two different ways of answering it, and how you choose to answer it. When you answer it, if you don't know what field you're in and you're somewhere in this, one of the two answers suggests you think number theoretically, and one then suggests you think geometrically. And so somehow people's brains work in different ways. And more generally, if you say what the odds are that it has no repeated m-fold or no nth power it has no factor which is a perfect nth power, always the answer, once the degree of the polynomial passes m, you always get the same answer. It's a single beautiful answer, but it's for a non-immediate reason. It's almost 1 minus 1 over p to the m. So once again, you get a nice answer. It's nice in a different way than the previous example I gave you. It's an answer that works in every single degree. It's like you got to 6 over pi squared. You got that answer by the time you by checking the first million integers. Okay. Next case, complex numbers. Now, something more reasonable to me. I'm not going to do the real numbers. There's a secret that algebraic geometers like complex numbers better than real numbers because basically you can solve. Well, there are many reasons why real numbers I find very confusing. X squared plus 1 equals 0 has no solutions. I find that very disturbing, and so I don't have these problems with the complex numbers. So many things work nicely with the complex numbers. The best way to describe the real numbers is, in my mind, in terms of the complex numbers, but I'm in a sharp minority about that, but we'll get to that in another 10 or 20 minutes. So for the complex numbers, let's now look at complex polynomials. And degree n complex polynomials, now each of these are complex numbers. And so now there clearly are infinite numbers, even if n is 1. An interesting point I want to point, a feature I want to point out about complex about this is that a polynomial of degree n is the same as knowing what its roots are. A monic polynomial, so having these this ordered n tuple of complex numbers is the same as the unordered n tuple of roots. So n unordered numbers is the same as n ordered numbers, which is it's hard to explain why that's surprising, but to me there's reasons for that to be surprising. And now, okay, so what are the odds that inside? Let me go back a step. Inside this space of if I choose n complex numbers, what are the odds that it doesn't have a repeated factor? And the answer is the odds are 100%. It's very rare for things to factor, so it's a very boring question. But that's not the right question. The right question, and how do you know what the right question is? The right question is the one that is somehow turns out to be parallel to the other ones. So the right question isn't exactly the odds. It's going to be about the shape of this space. So in complex, you have c to the n. So it's this big contractible, it's this vector space. But I don't want the entire vector space. I'm going to throw out where they have a repeated factor. Or maybe I want the fancier questions where there's an n-fold repeated factor. So now I get something which was nice and simple, a vector space, and I'm throwing out some very complicated thing inside it. And now we have a theorem from one of the mathematicians of the 20th century, Arnold, in 1969. And I'll tell you the example with not just with the square factor, but in general, that he says, well, he tells us about the shape of this space. And this seems like it's something different, but my point is that all these answers are, when you squint, they're going to be the same. That he's going to tell you about the kinds of holes this space has. And now I'm going to tell you, never seen topology, a little bit about topology, and all you need for what I'm about to say later in the talk as well, which is you can picture the shape of something that you can visualize. How do you get a hold of the shape of something you can't visualize that's huge dimensional? One way to do it, one way to measure it is you count the different kinds of holes of different dimensions in the space. And these are measured in some sense by what are called cohomology loops. And what Arnold says, the key thing is that once you take this vector space, which has no holes, and you throw out the polynomial, the subset of polynomials that have m-fold, that have factors, nth power factors, then you've introduced holes, but only one hole of one dimension, and there are no other holes. So that was so he knows really quite precisely what the shape of this space actually is. Okay, so maybe what's the miracle involved here? Well, maybe, how can I argue that there's a miracle? Really, there's a miracle because it's really surprisingly a simple space, that you throw out something complicated and gotten something simple. But the main miracle is, it turns out to be that that if you squint, this looks like zeta of 2. This looks like the other examples that I gave. Because the third example is my 0th example. The zeta of 2 example, I claim this is not polynomials, but I think the integers are very much like polynomials. But now you really have to squint to see why they're the same. So, okay, so my claim before I move on is that I gave you 3 things with 3 different answers. One was about number theory, and there's pi and zeta of 2. One was about finite fields and working mod p, and it was a 1 minus 1 over p, and one was about, and it was always 1 minus 1 over p. One was about the complex numbers, and it was about, and always there was just about this cohomology group. It's about the shape of this space. There were about 3. One was number theory. One was I don't know what you call it, finite fields, arithmetic geometry. One was topology, and later on I want to make these 3 all to be the same thing. And so to do that, I'd like to explain how to connect things. But before I do, let me just pause and ask if there's anything worth saying about those 3 examples. I gestured toward mysteries, and I gave no answer to explanations. I admit that. But if there's things I can say that will make you not happy, then that will make you less confused, at least. Then I'd be happy to.
Can you explain a little bit about the definition of HI?
I So I don't want to. Okay, so let me. To me, really, my picture of H1 is that there's a one-dimensional loop. There's a piece of string in this space that cannot be shrunk and disappeared to be nothing. There's one, and what this is saying is,
So it's not a simply connected. Something like that.
yes, exactly. If you want me to say more official, it's homology with rational coefficients. And so this is saying that there's the only right. So this is the failure of it being a vector space is contractible. It's simple. It's basically just you can shrink it down to a point without losing any. It's basically the same shape as a point. This is saying this is looking very much like really in some sense like a sphere. But the real, I mean, the secret thing is that this is really a zeta two. Like really, this is zeta. Well, this is something I'm not saying here. Are there more questions I cannot answer? Okay, great. So great. So let me talk about something else that I want to explain. Okay. So in order to begin, I just want to say enough about the language of algebraic geometry that you can follow what I want to say, or at least technically the terms are defined, but really it's the intuition which matters. But I want to have said things rigorously enough that you could at least accept that, and then you can let it go. So just to set up this background, let me just first start with the complex numbers. And so complex n space, for my own reasons, I want to rename C to the n, which is a perfectly good name, to something as affine n space. So the A just stands for affine. This is this is purely notational, but and the use of this notation doesn't pay off in this hour, but it goes off. But I want to say it. So the building blocks of complex algebraic geometry are what are called complex affine varieties. But really, all it is the things cut out by a bunch of polynomials. So, for example, in 3 space, that's 3 space, fine 3 space. You have this. I just wrote down a couple of polynomials, and they cut out something, whatever it is. I just say whatever it is. That's an example of a variety. So my definition is stuff cut out, an affine variety. So that's now you know what an affine variety is. And in general, what's a variety in general? You glue these things together, which are cut up by equations, and you imagine that there's one and there's another, and you glue them together. And the rules for gluing turn out to be things you can write down again just with polynomials as well. So that's all I need to say. Think of it as a new kind of space. Those of you who've heard of manifolds, a manifold is intuitively something which looks smooth, like a smooth surface is something. An abstract surface is something which is smooth, looks like a surface, and we say, well, locally, it looks like a little bit of things I understand, and they're all glued together. It's the same sort of thing. Now we're building blocks rather than getting little bits of stuff we cut out of fabric are going to be things, or instead it could be things we cut out by polynomials. That's all it is. It's a new kind of space that was in some sense invented hundreds of years ago, and in some sense invented in the middle of the 20th century. But maybe better than a definition is an example of one you've seen before that you already used to thinking, which is the projective line, P1, which parameterizes. So what does it parameterize? I'll tell you what it parameterizes: lines through the origin. So here's there's the plane, and I consider all the lines through it. And so what are the lines? If I said, what are the lines for the origin? How would you think about them? Well, most lines have a slope. They're characterized by the slope. So the slope is just B over A. Well, not all of them, because the vertical line doesn't have a slope, right? So everything but the vertical line has a slope. So the numbers are basically parameterized by n, by the complex number. The lines are parameterized by n, almost all. Okay, but not all. However, most of them are also parameterized by the inverse slope, by A over. So in this case, that has inverse n's. If m is rise over run, other is run over rise. And the inverse slope, that is inverse slope 0, but now it's a horizontal line that has no inverse slope. So most lines have an inverse slope, most lines have a slope. And all but one have a slope, all but one have an inverse slope, all but two have both. And we know how to relate them because 1 over this is that. So that is exactly what we built the notion of a variety for. We've taken one complex copy of the complex numbers. One copy of the complex numbers is, you know how to picture. We have another copy of the complex numbers. We glue them together, and we produce a variety. And you even know how to picture that. intuitively, you take your plane and your another plane, you take the two planes and you glue them like this, and what shape do you think you get? You can picture this. So, a sphere. Yes. So the complex. So we built the sphere as a complex. So all we're doing is formalizing something you've seen before, and now I'm going to introduce the things from the middle of the last century that made people's heads hurt, which is we want to do what the computer scientists were doing and work mod p, for example, and so we want to work over not just over the complex numbers. And so the definition is really similar, but there's a twist which I'm not going to fully say, but I do want to say enough to give you an idea of how the twist is. So the main difference is there's a richer notion of space, of just normal affine space. So it's not just, so the affine n space isn't just like complex n space is C to the what this is something richer. There are new kinds of points that are involved that I still claim you can sort of visualize. And so I'll just give you, I'm not going to tell you what it is, but I'll give you an example of how I picture affine about real space. That's why I don't call this RDA. It's better than RDA. It's richer and got more points. So what it is it's made, you can think of it as n-tuples of complex numbers, except that you're gluing an n-tuple to its complex conjugate. So my example, actually, can I grab a piece of paper? So for me, when I see it's the one-dimensional version, A1, the real numbers, I see as the complex numbers, except I glue every complex number to its conjugate. So I take the complex numbers, I glue everything with conjugate, and so the old-fashioned real numbers are there. But now I've got the complex numbers are there too, kind of just glued to each other like that. And that's my picture. So it's a richer version. The original stuff is there, and you've got a lot of bonus ones that are convenient to have around. And why? Well, there's a whole rich story. And so now at this point, you know what a variety is over any field. The one thing is you just do work in these more complicated spaces. So at this point, I've said this only to be scrupulous, and I wanted to let it go for a second and not worry about the fact that I've just defined this for you. And I want to now tell you about how you cut and paste geometric spaces. So it's a calculus for kind of adding, subtracting, and multiplying spaces. So here's my rule, and I'm going to say it in a way that's very formal on the screen, but in practice, it's going to be very simple. And I'm just going to do it by hand, which is I claim I'm going to tell you how to multiply and add spaces. So my rules for adding and multiplying spaces is, first of all, if I take a space and I can divide it into an big open part and a small closed part, and I'll leave a set aside because I know some people might not know what closed and open subsets are, so don't worry about it exactly. But if I break something up into an open and closed, my rule is that this is equal to this plus this. So I add things up by just cutting, ripping. It's if I had scissors, that would be better. The metaphor would be better. I just have the rule that I can cut things up into pieces like this. That's how I add. How do I multiply? Well, if I wanted to, I multiply spaces by multiplying spaces. If I want to multiply this one-dimensional thing by this one-dimensional thing, I take the result is the two-dimensional. So I multiply space. And that's it. That's my definition. And I just thought my definition there, and that's basically it. And so if I do this with varieties, I get the Grothendieck ring of varieties, but I can do this with anything. And with this seemingly stupid definition, I'd like to take it for a test drive and show you what this gives you. So the first thing I want to point out is that a point is 1, because it's like the number 1, because a point times anything is that anything. So like a point is that when you see 1, a point, you should think that's like 1. The empty set is like 0. When you multiply the empty set by anything, you get the empty set. So now you know what 0 is. And now the real numbers. Well, okay, I told you I don't like the real numbers, but I have friends who do. And they tell me that the real numbers, there's 0 is a real number. I heard that there are positive ones and there are negative ones. And so my rule for cutting for in this thing is that I take the real numbers. Well, that's equal to the negative ones plus 0 plus the positive ones. But the negative ones, so the positive ones are that's basically a copy of the real number. You can exponentiate or the real numbers to get the positive real numbers if you want. So, and similarly, the negative ones are also a copy of the numbers. And the 0 is a point. That's 1 in this. That's 1 in this. So the real numbers is really the real numbers plus 1 plus the real numbers. And I can solve that. And that means the real numbers is minus 1. So this looks dumb. So it looks like, and that means that r to the n is a minus 1 to the n, because that's how they multiply. Products are products. Okay, so this looks really dumb. But let me just point out something really non-trivial secretly, which is if you take a space, the more interesting space, here's X, which is a nice, beautiful surface that you could probably buy at some bakery. It's a genus 3 compact surface. And I said, what is it inside the space? Well, what I would do is I would break this up into pieces. And if you could see this map, if you could turn on, I guess I could try to change the colors here. Let's see if I can use that. Yeah, this is the power of modern technologies. I can now turn all these colors on. Now, red, the holes are supposed to be black. Give me So basically what I've done is I've taken this strange planet, which it's like the Artemis has discovered the strange planet in the dark side behind the dark side of the moon, and it's shaped in this way. And we settle this planet, we make countries on the planet, and every country is a nice, reasonable country that looks like R2, that's contractible. And so we've cut this thing up into a bunch of vertices, which are these points, a bunch of edges, and a bunch of faces. So we get the class. So in this ring, the class of X is equal to, well, each vertex gives 1. The edge is like a copy of the real number, so that gives minus 1. And each country face is like R2, so it gives a plus 1. So we get V minus C plus F. So what we get is that the class of axes we get is just cut it up into pieces and count the vertices, subtract the edges, and add the number of faces. And so this counters this famous formula of Euler, which says that on a sphere, no matter how you cut it up into countries, V minus C plus F is 2. Or the fact that there are negative surfs in genus G, V minus C plus F is 2, is some mysterious number which you use to define the genus. So the fact that there is this invariant is buried in simply, we seemingly done nothing, and we've discovered the notion of Euler characteristic. And so that's, in fact, what we've recovered and invented is the compact basic Euler characteristic, if you want to say something fancy. And there are lots of fancy questions, like I made the definition, but I haven't proved for you. It's not obvious, maybe. It's not at all clear that 1 is not equal to 0. And it's not clear that 5 is not equal to 0, for example. There are all sorts of things that are not immediately clear, but this connects something to important and fundamental facts in topology, and we got there by doing nothing besides simply making this definition. And okay, so we get this, and it's in some sense great. We got some fundamental thing in topology, but we don't see many things. This sees a lot of things. It sees the Euler characteristic, but it doesn't see a lot of things. So for example, a lot of things have value 0. The empty set has value 0. The circle has value 0 because I can break it up into 2 vertices and 2 edges, say. The torus is value 0. 2 circles together have value 0. So you don't really see, you can't read off anything. This has got 2 pieces. That's got no pieces. That's dimension 2. That's dimension 1. You don't see very much. But in algebraic geometry, now this I think is probably, I would put honestly, as one of the top 10 mathematical results of the 20th century. It underlays some things, but it's somewhat invisible, so people often don't know about it. It's the fact that something is algebraic means that there's way more going on than you would hope. And if you want, for the experts, this is Deligne's theory of weights, which is part of why he got the Fields Medal, was part of his part of this vast array of things that he proved. And I'll tell you a little bit about what this is. So if we're dealing with complex varieties, things we can talk about only with polynomials. So we're not allowed to do crazy things like ripping paper and old-fashioned cutting. You're only allowed to do things that you can describe in terms of polynomials. Well, then we can still do the same thing. We have this magical ring. And if we do things with the complex numbers, if I make only algebraic cuts, they're still cuts. So I still can read off this Euler characteristic. So it means that I can quickly, for example, pick off things like the complex projective plane. I can cut and paste it into 2 copies of C2, 1 copy of C, 1 copy of the point. And my recipe for rules immediately tells me that its Euler characteristic is 1 plus 1 plus 1 is 3. And I've magically computed something which would otherwise be hard to compute. But the point is that there's much more information. And you can recover not just the Euler characteristic, but so much more about it. You can recover the number of pieces it has. You can recover its dimension. You get much more than just a single integer's worth. We get so much more that we can name some things, but there's much we can't. There's even more we don't know how to read off. So for example, one example is if I have 17 beautiful algebraic spaces, and I cut them up and paste them in completely different ways on completely different things, I'm still guaranteed to have 17. And they're guaranteed to be the same dimension. They may be different, but there's way more conserved. It's a conserved, way more conserved quantities is the way I would describe it in the algebraic world than in usual geometry. And more strongly, now comes to the words I'm refusing to define. You can see not just the single integer, but you can count the number of holes. You can count the cohomology groups. So I'm just going to do this for you by example, which is the complex projective plane. This parameterizes. Just to be clear, because I have defined this, this is about lines in 3 space. This is the variety which parameterizes lines in 3 space. You can cut it up into 3 pieces. And I claim, I've not exactly told you the recipe, but it's largely what you might speculate, given what I'm about to tell you, tells you that I can tell you how many holes it has. It has a 2-dimensional hole and a 4-dimensional hole. And it's got 1 piece. That's what these things mean. And it has no other holes. And all that, again, I've not, Gordon asked me to define cohomology, and I've not defined cohomology, but the point is that it is measuring something. And this measuring of different types of holes, whatever this complicated thing is, the thing you can't visualize, we pick it up really easily by being able to cut this up into pieces and have things we absolutely do understand, like the complex numbers. So that's part of what the magic that this gives you. But it gives you even more, because if you do this, not just with the complex numbers, you could think like a computer scientist and work with a finite field. And there you can do something just like we counted things. You could count off the number of solutions in that finite field. And so, for example, what does that mean? It's like if you said, what are x squared plus y squared equals 2, and you wanted to count solutions mod 3, you just count solutions mod 3. You say, oh, there's 4 points. And this thing behaves very well with cutting and pasting. So counting solutions also behaves well. And counting points looks very different than counting holes in different dimensions. But nature is trying to tell us something. We're getting exactly the same kind of information, and that they seem sort of cognate to each other. And so really that point counting is like a kind of Euler characteristic. And this leads us to what are called the Weil conjectures, which were proposed in the first part of the 20th century, or the mid part of the 20th century, and were the motivation for the creation of a good chunk of 20th century mathematics, behind which I guess Falting's got the Nobel Prize this year, and this led to the conjecture that he proved that when the Field's method, they were the Nobel Prize, that this parallel between just counting points and not being able to pick off and the shapes of things over the complex numbers comes directly from him. And now I told you I was going to give you 4 examples, and if you counted carefully, I only gave you 3 examples at the start. So this is the 4th, which is we're interested in the set of degree n monic polynomials, and we're wondering about those with a multiple root, or a multiple, what I really mean is a factor, a multiple power, a high power factor. And the answer, so the fourth thing which parallels the others is that you take space of degree n polynomials, that's n space. You throw out something very complicated, which is those polynomials that have an nth power factor. You get something very complicated left. You have a very weird thing left over. You can cut and paste it in such a way. It's like I even have I brought 10 grams to UConn. I was going to bring them, but I didn't bring them here. It's like a 10 gram. You just cut them into pieces and rearrange them to get n minus m space. And that is that's the reason why when you divide all the polynomials without an n-fold root divided by all polynomials, you get something. Well, what does this mean? The main thing is that you see something which looks, if you squint, looks just like many of the other examples. It implies many of the other examples. It makes you want to see a zeta function if you know that. Okay, so then the story generalizes widely, and I'm going wildly, and this is only, I feel like this is the foothills of a mountain range, but it gives you a sense of how you might want to study different kinds of spaces by understanding points on the spaces, equations on the spaces, polynomials on the spaces, and the right way to either prove things about them or get conjectures about them are you can do it by either counting points and doing computer experiments. You can do things by cutting and pasting. You can do things by getting a hold of cohomology groups, and you can do things with zeta functions. And if you prove anything in any one of these worlds, it suggests parallel theorems and sometimes implies parallel theorems. Okay, and I'll conclude by applying these in a different place. But let me pause because I think let me just say what I've done in the previous section, which is we have this recipe, this sort of maybe this tool of we have this world we want to live in, any kind of space we want to deal with, be it topological spaces, reasonable manifolds, or algebraic spaces, pieces of paper, 10 grams, one of the Hilbert problems fits under this rubric as well. You can make this ring, you can make this algebra of your spaces by adding, you know how to add, subtract, and multiply. And then you can do calculations of this ring and the theorems of this ring. And these examples, and the definition is easy, but the consequences are really quite deep, going from topological things and even conjectures. And let me pause to see if there are any things I can say that will either help with confusion or give you added interesting confusion. Okay. I'll read this out. Okay, so let me conclude by telling you about Bott periodicity. And here I will frankly tell you that my secret goal, if you do nothing more than hear the story of Bott periodicity, you've never heard it before, this is like just a pleasant story to know about. And the fact that it relates to algebraic geometry to me is, icing on the cake. That Bott periodicity is this amazing thing. It's one of the fundamental results in topology and K-theory, and it's discovered by Bott again in the 20th century. And the way in which it's historically thought about, it's important thing is related to physics and it's the foundations of K-theory. And the way in which it's thought about, partially, I think, mainly because the people who invented it thought this way, is that it's very analytic in nature. Like the proof involves lots of T's and differentials, other symbols that I find very confusing sometimes. And it looks like it's fundamentally analytic in nature. But I feel like whenever things are really fundamental, they look like they come from something kind of deeper, like further back in the evolutionary tree, go back before algebra and analysis, separated into different animal kingdoms. So what is Bott periodicity? Well, here's how I think about it to begin with, which is imagine, so consider 100 by 100 orthogonal matrices, about what you mean. 100 by 100 matrices. These are now we're in real numbers. Matrices where all the rows are 100 tuples of unit vectors in 100 space. So, of course, you can't picture it, and I have no example for you. So I have an example here, but it's too big. It's under the desk. I have a 100-dimensional vector space, and I have 100 orthonormal vectors, vectors mutually perpendicular here. So there's one. So it's a single here. They're mutually perpendicular, and they're the columns of the matrix. So consider all such space. They form a space. So that's topological space. You could imagine asking about the space. And one way you get a hold of space are the cohomology groups, which we described, but there are also homotopy groups, which I'll say are, they measure whether you can map spheres in. So what this means, what this pi 12 means, is that when you try to map any 12-dimensional sphere into it, you can always contract it. Whereas 11-dimensional spheres, you actually can't contract it. There's like an integer's worth of ways of fitting an 11-dimensional sphere. That's not a definition, but maybe good enough that it's a way of measuring the types of holes in it. So you could imagine that you could write a computer program that would compute this by hand, some huge painful thing in this huge dimensional space, and you discover that these groups are of the following form. And what really matters is the pattern you notice, which is for some reason you get these things, and who knows what that means, but then you get the same thing, and then you get the same thing. And that's when your mathematical intuition kicks in, and you think, okay, maybe this goes on forever. And it turns out that it does not go on, which is the only thing better than a pattern is a pattern that stops eventually, because it's got to stop for a reason. There's a pattern that wants to be true, and there's a reason why it's not being true. So what do you guess is happening? What you have to guess is happening is that 100 is a nice big number, but it's not big enough. And so it is true that if you increase 100, the value of 100 by a little bit, these numbers all stay the same, but the pattern goes a little bit further. And so your guess should be that what it really wants to do is that there should be, as the numbers get to infinity, this is just like the initial question of how many integers are square free, that there should be some best infinite dimensional thing. And then it really does, it does repeat mod every 8. And you should guess that the reason 100 is an imperfect reflection of this perfection. But the 100-dimensional one kind of maps to it and seeing everything up to a while, but then it's not big enough to see it. So that's what you should guess. And so Bott periodicity is about this eightfold repeat. And then as a mathematician, you abstract away one further time. And what if you're someone like Bott or Atiyah, you realize that the right notion is you have O infinity, and that there are in fact 8 different spaces in a row, not just this one, but 8 of them. And each one involves mapping loops into the next one. So the explanation for an eightfold, the one explanation for this eightfold thing is that every time you map, you replace a space by mapping the space that loops into it, it turns out you shift those numbers over by 1. So if that's true, then you might guess that if you do this 8 times in a row, you get the same thing back to where you started. And if you continue to be an optimist and a strong believer in the injustice in the universe, you would have then, if you do start someplace and 8 steps later to get back to where you started, you would think maybe every single step in your path must mean something important. And in fact, it does. And then what Bott periodicity says is that there are 8 magical spaces in a row. Each one is obtained from the previous one. That is the explanation. And then maybe you discover the little brother to the big. But there's a little brother to this as well, which I will call complex Bott periodicity as well, and that these are the reasons for this going on. And so somehow I love this about mathematics, that you walk out in the world, you notice, like the string between 2 poles hangs like this, and you say, aha, that makes me think this, which leads me to that, which leads me to that. But at some point you're flying beyond the moon, because of what you managed to figure out. So each step leads you to the next one. So I think I'm nearing the end of my time, so I think now I want to simply say that the proof of this involves some, what I think is very clever and smart analysis. And you shouldn't have to be clever and smart. You should just have to be patient and just patient, think about it the right way. That there should be some naive algebraic versions of these spaces, that where it's not about the complex numbers, it's about even the integers, if this makes sense, where everything has a very simple meaning, And then when you say things with enough generality, the proofs become simpler and not more complicated. And then once you have the right picture and it has a very simple explanation, you can take the complicated answer as a specialization by thinking about it in a special case. And so the thing I just wanted to show you is that somehow in the end, this is the little brother. The big brother takes more to say of the two Bott periodicities. The little brother of Bott periodicity can be summed up in a simple diagram. It's less not going to explain what this diagram is, and more just that the simplicity of the diagram kind of shows that it's like when you see these table things like in physics, the elementary particles, the standard model gets simpler and simpler. The more the standard model is this radical simplification of really messy things that seem really messy. If you look at it just the right way, in a very small number of symbols, you capture the essence of what's actually. So let me sum up, and then offer you a chance to catch your breath and also ask questions. So what happened is, all that matters is there's this way of thinking which partly is central in algebraic geometry, but is certainly used in many other fields. But some other questions that seem to lie fully within theory of numbers. There are other questions that are fully within geometry or fully within topology. But the thing about mathematical knowledge is nothing is fully. Actually, there's even probability present here, as you might have noticed. There are a couple of other fields that were certainly combinatoric. So the way in which the proofs are done involves some combinatorial things which were probably seen as sophisticated decades ago and are now absorbed into it. That really things that seem very different points of view, you should almost take a step back and see them as somehow simpler and simpler the more steps you take back. So thank you very much for your time, and I hope this gave you some glimpse of how I think.